Hello, welcome everyone to day 4 of the Internet Computer BUIDL Bitcoin Hackathon sponsored by Encode Club. It's so nice to see you as every day, and it's very nice to see people returning for more workshops. Today we have two very special workshops. The first one is now by Yan from Rocklabs, who will be telling you about connecting to EVM from ICP Canisters. Then in about 45 minutes in the same event, we'll be joined by Ihor from Orally, who will tell you something about harnessing a fully centralized and efficient oracles for cross-chain usage on the ICP blockchain. But for now, I'm glad that you are here. And yeah, no more info from me. Jan, feel free to share your screen and start the workshop whenever you are ready.
Okay, so yeah, hello everyone. I'm Yan from Rocklabs, and today my topic is about connecting to EVM blockchains from ICP Canisters. And in fact, we in Rocklabs we have been building Ethereum integration for a while, and we built a set of tools and products to connect to EVM blockchains. And yeah, the content today will be two parts. The first part is on how to use our IC Web3 library to connect your canister to EVM blockchains. And the second part, I'm going to introduce our project Omnic and explain how it works, how it connects EVM blockchains with the Internet computer. Okay, so I'll do a quick background introduction on the Internet computer. And as you can see, the Internet computer is applications on the Internet computer run in canisters. Canisters are smart contracts on the Internet computer. And the difference between canisters smart contracts with other blockchains is that canisters can make HTTP calls, which means that you can fetch or post data from or to other blockchains within the canister. And the second very important feature that the Internet computer provides is that canisters can sign messages via threshold ECDSA, which means you can sign transaction of any blockchain with ECDSA support. Okay, so these are the most important features we are going to be used in the following content. Okay, so what is IC Web3? Basically, it's a Rust library that helps you to connect your canisters to EVM blockchains, as the picture shows on the right side. You can, IC Web3 is a SDK, canister development SDK. You can use that SDK to fetch information from EVM blockchains, and you can use the SDK to sign EVM transactions through threshold ECDSA provided by the Internet computer. And you can also send the signed transactions to EVM blockchains using IC Web3 library. Okay, and another option to connect to EVM blockchains is through the endpoint canister. The endpoint canister is the Ethereum phase 1 integration proposed by the Internet Computer Foundation. And as the picture shows, it's basically a proxy canister, helps you send RPC requests to EVM blockchains. And your canister can construct the raw RPC information and send the RPC request to the endpoint canister. And of course, with you have to attach cycles with your request, and the endpoint canister will then access the EVM blockchain RPC endpoint and fetch the information and return the result to your application canister. And currently, it's already deployed on the intercomputer mainnet. This is the canister ID of the endpoint canister. And okay, so how can you use IC-Web3 or the endpoint canister? I'm going to switch to okay. Is everything okay?
Yes, we can see it.
Yeah, okay. So this is the GitHub repository of the IC-Web3 library. And we have in the example folder, you can see there are two canisters, one endpoint canister and one example canister. Let's first go over the example canister. In the example canister, you can basically there are many functions. For example, you can fetch a block from Ethereum, and you can get Ethereum gas price and get the canister address, and you can get transaction count, and you can send Ethereum transactions. And I'm going to explain the code a bit, and I'm going to actually execute this requests and show you how it works. So let's quickly go over the code. In this section, you can see there are some constants. You have to define the RPC endpoint URL. We are using Goerli test title, and the chain ID is 5. And since we are on mainnet, the threshold ECDSA K name should be tested K1. This is very important. Otherwise, you wouldn't be able to generate a valid Ethereum TE-CDSA signature. And the first function is very important. I want to remind everyone to add this function to your canister, because the function has to be called transform. And the purpose of this function is to take the HTTP response and remove the response header and return the response. This is to avoid the replica consensus issue. Okay, and for example, you can the get block function. You can give it a block number, and it will fetch the Ethereum block from Goerli testnet and return the result. Okay, so let's see how you can how to do it. So first, you have to instantiate a Web3 object, and inside the Web3 object, there are a set of APIs. So you can web3.is.block, and you provide block ID, and you can fetch the corresponding block content, and it will return the block in a string. Okay. So these are all getter functions. Basically, the workflow is are all the same. You have to create a Web3 object and then call the RPC API. Okay, so and this one is I have to mention it because every canister, through threshold ECDSA, every canister can control a not just one address, but multiple address on Ethereum. And SE-Web3 library provide a function called get ETH address to generate a Ethereum address controlled by the canister. Okay. So through this endpoint, you can generate a Ethereum address for this canister. We are going to be using this Ethereum address to send transaction to Ethereum. I'll show you how to do this later.
Sorry,
okay.
Sorry, Yan, to interrupt. Could you just zoom in the code a little bit? People seem to be having problem with seeing it.
Okay. So can you see it now?
Yes, I think this should be better. Thank you.
Yeah. Okay. And yeah, there are different examples. I'll go to, yeah, you can, actually SE-Web3 is based on the Rust Web3 library. So it supports all the features Rust Web3 library provides, plus threshold ECDSA. So yeah, you can make batch requests to Ethereum RPC providers. This way, you don't have to, through batch requests, you don't have to wait too long, because when you are using batch requests, the RPC requests are sent to the RPC provider in a single HTTP call. So this is going to be faster. And this is the send is function. Basically signs a Ethereum transaction and send some Ethereum to the address 2, and you can specify the value you want to send. You can specify the length of the address that the canister controls. Okay, so so you have to specify the derivation path and the key info related to the account you want to use, because every canister can control multiple addresses on Ethereum. So you have to specify which account you want to use through derivation path and key info. And once we have that, we can calculate the canister Ethereum address. Okay, and then we instantiate a Web3 object. It's a HTTP client to access Ethereum RPC providers. And before you can send your transaction, you have to get the transaction count, which is the length of your address, the from address. Okay, so you can also provide this value here, but it's optional. If you don't provide it, the canister will fetch it through HTTP call. And then you have to put these parameters into a transaction, and then sign the transaction. We in SE-Web3 library, we incorporated the threshold ECDSA sign process to the sign transaction API. So you can use it like you are using Rust Web3 library. The APIs are all the same with Rust Web3 library. And after you sign the transaction, then you have to call the send raw transaction API to send the transaction to Ethereum blockchain, and it will return the transaction hash. Okay, so this is how you make transaction from inside the canister to Ethereum blockchain. And later I will show you how it works. Okay, and you can this is not limited to this. You can also call a contract. For example, you can query your token balance, which is calling the balance of function of a token contract. And you can also call the contract function called transfer or transfer from to send token. The workflow is pretty much the same with send is. The only difference is that here you can see you have to when you are calling a contract method, you have to first instantiate a contract object here. You have to provide the Web3 object instance, and you have to provide the contract address and the related contract API. In this case, we are calling a ERC20 token contract, and it's the token API. And then you can, in this case, we are sending some token from the address, this canister controls, to some other address, this to address. So you have to, there's an API for this called signed call, okay? Signed call transfer, and specify the to address and specify the amount you want to transfer. And then, the transaction will be sent and it will return the transaction hash, okay? So this is the pretty much the example canister, and now I'm going to try to call these APIs and show you how it looks. Okay, switch to another window. Okay, this is my terminal window. Can you see it?
Yes, we can.
Okay, so I've got two canisters deployed on the Internet Computer mainnet. The first is the endpoint canister. I will talk about it later. And the second is the canister is named ETH, which is the example canister I just presented. Okay, so it's already deployed and with the latest version. We can let's see what do we have here. I can get some we can try to fetch a block from Ethereum blockchain. Let's try this. You have to provide a block number for this API. You can try. So let's try to get the block with the height 1 million. Okay, so this is on Ethereum Goerli testnet. Okay, so let's call it, see how it goes. Okay, so this is the block returned in string format. You can see it. It's a Ethereum block header with a transaction list. Okay, so and we can also try to get the gas price on Goerli right now. Okay, so this is the gas price currently on the Goerli blockchain. This, and then let us try to send a transaction to the Ethereum blockchain. First we have to check the canister's Ethereum address. Get canister address. This API will return the address that this canister controls on the Ethereum Goerli testnet. This is the address that the canister controls, and since I've already deployed this canister and I tested a few hours ago, and I already have sent some Ethereum to this address for gas fees. Okay, so now we can let's first check how many Ether are in this. We can check the balance of this address that the canister controls. Okay, so it's this much. It's about 0.042 Ether in this account, and now I can send some Ether from this account. This account is controlled by the canister, and I want to send some Ether from this account to another account. Okay, so let's send some. The first parameter is which address you want to send the Ether to, and the second parameter is the amount you want to send, and the third parameter is the length of the address that the canister controls. And if we don't provide length, you can just fill in now, and the canister will automatically fetch the length through HTTP calls. Okay, so let's see how it goes. Yeah, it takes some time because while we are waiting, I'll try to explain the process here. So when you send this request, the canister will first fetch the length of the. Okay, so yeah, it's pretty fast indeed. So it will fetch the length and fetch the gas price, and then construct a raw transaction and call the threshold ECDS API provided by the intercomputer to sign the transaction, and then send the transaction through outbound HTTP call to the Goerli blockchain, and it will return a transaction hash. Let's check. I'll switch to the browser to check this transaction hash. Let's see. Okay, so can you see my screen?
Yep, this perfectly visible.
This is the address that the canister controls. Okay, you can see that I've already sent some test transactions through the address. So it's all sent from the canister and signed through ECDSA calls. Yeah, we just the Explorer sometimes the data the syncing process takes some time. Okay, let's let's not wait. We don't have to wait it, and I'll continue to to the endpoint canister. That's about the example canister. The example canister basically shows you how to use these APIs provided by the IC Web3 to fetch information from EVM blockchains and send transactions to EVM blockchains. And yes, basically you can find anything you want if you want to build with IC Web3. Okay, so and the second canister is called the endpoint canister. This is the product proposed by the Divinity Foundation for the Internet Computer and Ethereum integration phase 1. Basically, it provides a proxy canister, which we call Endpoint Canister, and it provides a very primitive API for application canister called JSON RPC. Okay, so you can send raw JSON RPC request to this function from your application canister, specify the payload, which is the JSON RPC payload, and specify the target. The RPC target is essentially the RPC provider you want to use. And you have to also specify the max response byte to save cycles cost. If you do not specify this value, it will be defaulted to a very large value and cost a large amount of cycles. So we encourage everyone to, if you want to use this API, you have to provide this value. And because HTTP calls consume cycles, so you have to attach cycles when you call this API. And it will calculate the it will estimate how many cycles will this request consume and return the exceed the amount of cycles to your canister. And so basically the endpoint canister, I have to clarify that the endpoint canister does not rely on ICWeb3 library. ICWeb3 library is basically just, you can see it as a wrapper around RPC endpoints. It provides a set of easy to use APIs for you to interact with EVM blockchains. But if you want to work with endpoint canister, you have to construct your own raw RPC request. Okay, I also show you how to call this API. Okay, let's check. I'll show you how to call the endpoint canister. You can, in this case, I'm calling the JSON RPC method of the endpoint canister. I want to query the current gas price. So you have to provide the string format of the raw RPC call. And you have to specify which RPC provider you want to use. In this case, I'm going to query the gas price of the Ethereum mainnet, and I want to use the public load RPC provider. And let's see. You also have to attach some cycles to call this API because it will consume cycles. Okay, so it's already returned. The result is in hex format. You have to decode this result yourself. Let's continue on our slides. That's about how you can use ICWeb3 and how you can use the endpoint canister to connect to Ethereum blockchains. And for there are some reminders. Also, you can call it best practice. So first, you have to avoid replica consensus issue. I mentioned in the example canister, you have to add the transform function to your canister. And the second thing is to avoid consensus issue, you have to fetch the block height before you query any information from EVM blockchain. The best practice, you fetch the block height first, and then for the later RPC request, you specify the block height, and then you can avoid the replica consensus issue. And yeah, for some especially financial related applications, to ensure that the data you fetched from external RPC provider are authentic, you have to, yeah, we advise to fetch from multiple RPC providers and compare the result. And for sending transactions to Ethereum, first, there are typically 3 steps. So you sign the transaction and send transaction to the Ethereum blockchain through HTTP call, and then you query the transaction result. So basically, you have to perform 2 HTTP out calls. Yeah, that's about ICP and the Endpoint Canister. And for the second part, I'm going to quickly go through Omnic. So Omnic is obviously using ICP as its foundation, and the purpose of Omnic is to build a scalable and programmable cross-chain messaging protocol based on the internet computer. Basically, it turns the internet computer to the layer 0 of Web3 ecosystem. And this is how Omnic works. It's the basic architecture of Omnic. So we can connect to multiple EVM blockchains. In fact, not just the EVM blockchains, but all blockchains that support ECDSA signature. But we are starting from EVM blockchains. And there are a set of gateway canisters responsible for fetching cross-chain messages from EVM blockchains. And they will send the cross-chain message to the proxy canister. And the proxy canister will then notify the application canisters. And application canisters can also send cross-chain messages through the proxy canister to the Ethereum. So this architecture is fully on-chain. So yeah, it basically connects. You can connect all the EVM blockchains to the internet computer. Yeah. And okay, so another important feature of Omnic is that it's programmable, because you can incorporate your application specific message processing logic into your application canister. For example, you have a application and have parts running on Ethereum and running on Arbitrum. You want to communicate. These parts want to communicate with each other through Omnic. And you can also deploy a application canister on the internet computer to perform custom message processing logic. For example, the Ethereum contract is sending a cross-chain message to Arbitrum. When the message reaches Omnic, and the Omnic will notify the application canister about this incoming message, and the application canister can perform your customized message processing logic, and then send the message to Arbitrum. So due to the time limits, I'm not going to go any deeper in Omnic, but we have, if you want to use Omnic to communicate through your different your contracts running on different blockchains, you can check out this example. It's a Omni-chain token example built on the Omnic message passing protocol. And we also built a token bridge based on the Omnic message passing protocol. And the Omnic scan displays all the transactions happened on Omnic token bridge. We also have a JS SDK for developers to query your cross-chain message status. That's pretty much it for today. Yeah, just right on time.
Amazing. Thank you,
Thank
Yan,
you.
for the wonderful workshop. It was a very informative workshop, and I hope everybody enjoyed it as much as I did. Before we move on, there are a couple of questions.
Okay.
Victor is asking to go back to endpoint canisters. So canisters can make HTTP calls, and it is verified that several replicas receive the same reply. Do endpoint canisters differ in some way from this?
Let me check. Yeah. So, the verification process is processed by the underlying architecture of the Intel computer. So in the subnet, if you send a HTTP request to the subnet, and all the nodes, for example, 13 nodes in the subnet will perform the HTTP call and compile the results, and then return the results to the application canister. And that I also mentioned that if you want to, if you want to ensure that your the data you fetched from external blockchains is actually authentic, you have to fetch from multiple RPC providers. So this is a different level thing. This means you have to perform multiple RPC calls to external RPC providers and compare the result inside your canister. This is to avoid single point of failure. For example, if you only fetch transaction information from a single RPC provider, it might have a single point of failure problem. Okay, so this is what I mean here. It's different. Okay.
Cool. Thank you. I hope that answers your question, Victor. The second question that popped up is from Artem, who is asking, does Omnic already work with Cosmos? Is it possible to send Atom and exchange Atom and ICP tokens?
It's current. Like I mentioned earlier, basically Omnic can support any blockchain supporting ECDSA signature, but we are starting from EVM blockchains because EVM blockchains has the largest developer ecosystem right now. So technically in theory we can integrate Cosmos, but not yet.
Okay, I think that's pretty much it for now. I don't see any more questions. I think we'll wrap it up here. Thank you once again, Yan, for the wonderful workshop. It was truly a beautiful piece of teaching, and we hope that everybody enjoyed it as much as I did.